Welcome. This is the schematic representation of a functioning petroleum system. In this and the coming clips, we will go through it. At the end, you will have a good idea of how to predict the occurrence of hydrocarbons in the subsurface. Everything starts with a source rock. A good source rock has a high total organic content, usually more than 1%, and has been heated enough to generate petroleum. 3 stages are then needed to obtain in a high-quality source rock. Sediments rich in organic matter must be deposited. The organic matter must be preserved during subsidence, and the rock must be heated at high enough temperatures. This is more complicated than what it looks like. Abundant organic matter is generally produced in swamps as well as in marine environments. In these places, oxygen, light, and nutrients are abundant, making it possible for flora and fauna to thrive. These living organisms, plants or animals, form the organic matter you will find in the source rock. The next and possibly more difficult challenge for nature is to preserve the organic matter that has been deposited. The big enemy of organic matter is oxygen, which oxidizes and destroys the organic matter. The process is called oxidation and implies that oxygen is consumed to oxidize the organic matter. The system works like a candle. As long as oxygen is available, the flame will burn and oxidation will continue. For our purposes, this means that the organic matter will be oxidized and will disappear. This is what happens to more than 95% of the organic matter deposited in sediments. If, however, no new oxygen can be added to the system, the flame will consume all the available oxygen and will then die out. Oxidation has stopped. In our analogy, organic matter will escape oxidation and will be preserved. Zones with no oxygen are called anoxic. Where do these anoxic zones form? We can then predict the occurrence of organic matter depth if we are able to identify the environments with anoxic conditions. In swamps, most of the organic matter is created by plants and organisms living at the surface. When these die, they fall to the floor of the water column and get oxidized, creating anoxic conditions. With persisting subsidence, the sediment rich in organic matter will be buried and will not experience oxidation as the entire environment is anoxic. If these conditions persist, thick succession of potentially good source rock are created. Anoxic conditions are also present, though not common, in the marine environment. An important example is that of isolated marine basins. The most famous example is the Black Sea. The Black Sea is a deep basin surrounded from nearly all sides by continental masses and with only a narrow and shallow connection with the Mediterranean Sea along the Bosphorus. 2 types of waters enter the Black Sea. Large rivers bring huge amounts of fresh water and a limited amount of very saline water coming from the Mediterranean. In a vertical section across the basin, you can see that the saline, heavy water entering from the left will immediately descend to deeper levels because of its high density. The fresh water from the rivers, on the contrary, is lighter and will then remain at the top of the basin, forming a lid. The water column is thus stratified and little vertical movements will take place. This means that no oxygen will be delivered to the lower part of the water column, which will then become anoxic. Living organisms thriving in the upper part of the water column will, upon death, sink through the water column, experience oxidation, and will pile up on the basin floor. Similar situations, although at smaller scales, are common, for instance, in small basins developed during the early stages of rifting. In frankly marine regions, for instance along passive continental margins like the one shown in the slide, an oxygen-poor zone is at depths of several hundreds of meters, caused by the decay of organic matter from the organisms thriving in the upper part of the water column. If the anoxic zone persists, organic matter sinking through the water column and reaching the sea floor in this depth interval will be preserved and form potentially interesting source rocks. In previous slides, we have seen that organic matter can only be preserved in basin floors with anoxic conditions, and that anoxic conditions are destroyed by strong currents. These conditions were particularly well developed in some periods during the history of the Earth. If we look at the Earth during the Cretaceous, that is around 80 million years ago, we see a large ocean elongated in east-west direction, bounded to the north and the south by continental masses. In a north-south transect from one pole to the other, you can see that temperatures in the ocean were higher than present, and even more importantly, temperature gradients in north-south direction were very low. All this resulted in weak currents and a stratification of the water column. The Cretaceous was also a time of very high sea level, which caused the inundation of large continental domains and the delivery of large amounts of nutrients to the marine domain. A lot of nutrients, poor vertical ocean circulation, ideal conditions to form high organic content rocks. No surprise that a very large portion of world petroleum has been generated in Middle Cretaceous rocks. Welcome! We've seen in the previous clip how sediments with high organic content are formed. Large molecules of organic matter called kerogen are trapped into the rock. However, if these sediments remain close to the surface where they have been deposited, no petroleum is created because kerogen cracking only becomes efficient where rocks reach a higher temperature. In the plot, two curves are shown, one for oil and one for gas, indicating the temperatures at which cracking of organic matter becomes efficient. At temperatures below 70 degrees, reactions are so slow that the rock rich in organic matter will produce no significant amounts of hydrocarbons. The rock is named immature. If the rock subsides at deeper levels, kerogen cracking will occur and hydrocarbons are produced. The rock is called mature. Oil generation reaches a maximum between 70 degrees and 100 degrees. This interval is called the oil window. When rocks subside even more, they acquire even higher temperatures and production of oil will end. Rocks have become overmature. At the same time, generation of gas is still very efficient. The gas window is indeed deeper than the oil window. As you can see, determining the time temperature evolution of the rock is of great importance. The hydrocarbon molecules generated during cracking will initially be stored in the source rock. Storage will mainly take place in microfractures and in the little porosity left after sediment compaction, and will continue until the source rock is fully saturated. How do we then determine if we have a productive source rock? Seismic images do not provide obvious answers to this fundamental question. The first step is then to predict the presence of a rock rich in organic matter at depth. This is typically done combining geological models, regional knowledge, and a detailed analysis of seismic data. The second step is to predict its thermal evolution. How mature is the rock? If at all, when did it produce hydrocarbons? To predict the degree of maturity of the potential source rock, you will have to estimate its temperature. To do this, you need to predict the geothermal gradient. If temperatures follow the red line, temperature of the sediment will be between T3 and T4, and the rock will be overmature. Too late. The rock has subsided beneath the oil window and no more oil is being produced. If temperatures are controlled by the gradient shown with a blue line, then the source rock will be at temperatures between T1 and T2, and the rock is mature and fully producing. Timing is important. If the rock enters the oil window before the trap is formed, then the hydrocarbons will migrate to the surface, forming seeps and being of little use. If, on the contrary, the trap forms before or during petroleum generation, then a substantial part of the hydrocarbons will accumulate in the trap, forming a reservoir. In the next clips, we will learn more about these processes. Welcome. In the previous module, we have left the large petroleum molecules trapped in the source rock. These molecules will leave the source rock and flow along permeable layers until they reach their final destination, the reservoir. We will now discuss the main processes driving these movements, namely buoyancy and capillary pressure. Buoyancy is the pressure exerted on a mass with a density different from that of the surrounding. It is directly proportional to the density difference between the two fluids and to the height of the moving fluid. How big are density differences? How strong is the buoyancy motor? The plots in the slide show the densities of oil and gas at a range of temperatures and pressures. The latter is proportional to depth. A first-order message of these slides is that densities of oil and gas are substantially lower than that of water. This means that hydrocarbon will move upward. While moving upward, oil will become heavier and the density difference with water will decrease. The density of gas, on the contrary, decreases with depth, making movements of gas even more efficient. Flow of a fluid medium through a porous rock is resisted by capillary forces. The capillary pressure depends on chemical and physical interactions between the fluid and the surrounding medium and is inversely proportional to the diameter of the pores. The first step the hydrocarbon molecules will have to do is to get out of the source rock. We call this primary migration or expulsion. Primary migration will proceed slowly as pores are very small and the column of hydrocarbons very small. As soon as the hydrocarbons will enter the permeable rocks, they will travel much faster, with their movement being favored by much larger pores and an increase in hydrocarbon column. Following lines of highest gradient, petroleum drops will move upward, eventually end up in the reservoir, or, if the trap is not encountered, at the surface of the Earth. How fast are hydrocarbons moving along the permeable layer towards the reservoir? For this purpose, we use Darcy's law, which describes the flow of a fluid through a porous medium driven by pressure differences. As you can see from the equation, flow is inversely proportional to viscosity, which means, for instance, that oil will flow more slowly than gas. On the other side, flow is directly proportional to the pressure difference and to the permeability. Viscosity and pressure differences can be measured. The big unknown is the permeability K. Permeability is defined as the ability of a fluid to flow through a body of rock. Predicting permeability values is not easy. If we look at the vertical axis of the plot in the slide, you see that permeabilities of different types of sands vary up to 10 orders of magnitude. The problem is made even more complicated by the fact that hydrocarbons, in their tens of kilometers long journey from the source rock to the reservoir, will travel across very different lithologies. The permeability of large bodies is of interest to us, not that of small samples we can measure in the laboratory. Predicting permeabilities in buried, inaccessible, large body rocks is very challenging.